The Aerospace Experimental Payloads Team, or AXP team, is one of two teams working on this project. The other team, the Big Red Satellite Team, or BRS, is composed of about 14 middle and high school students from eastern Nebraska. For CubeSats in orbit, the only means of power is the sun. However, half of the Earth's orbit is spent in darkness, and many CubeSats fail because their solar panels degrade over time. An emerging type of solar panel, called perovskites, are a thin alternative to typical photovoltaics that offer higher efficiency and collection ability. Nebraska's Big Red Satellite Team will test perovskites' efficiency, lifetime, and light collection on the dark side of the Earth compared to silicon panels using a 1U CubeSat. We also aim to engage middle and high school students with STEM and launch the first CubeSat ever from Nebraska.
Big Red Sat 1 will be testing a payload of perovskite solar panels. What makes a perovskite solar panel special is that it has a chemical called perovskite inside of it. The chemical formula for perovskites is ABX3, where the A and B are cations, like methyl ammonium and lead, and the X3 is a halide, like iodine. When you put the perovskite chemical onto these solar cells, it increases the efficiency of the cell. It also allows the perovskite solar panel to collect light in low-light environments better than a normal silicon cell. Our payload, Big Red Sat 1, will feature silicon and perovskite solar panels on each face, in a way that will allow us to test the relative efficiency and light collection ability of perovskites compared to silicon cells. Once we complete this experiment, we will be able to tell whether perovskites are truly the future.
The secondary mission for our CubeSat is to demonstrate satellite-to-satellite communication while we are in orbit. The way we are doing this is by working with two different CubeSat teams, one from Florida and one from North Carolina. When we are launched from our rocket, we are planning on being launched together, and while in orbit, we will be sending and receiving data packets from each of these CubeSats. First off, to demonstrate students at our level are able to accomplish this task, and to provide a secondary means for payload data communications in the case of that one of our main Globostar radios fail.
In space, silicon solar panels are just about everywhere. They're on most satellites, they're on the ISS, and they're even on Mars rovers. Because of that, silicon solar panels are the standard to be compared to in space, which is why we're testing them against perovskites.
While silicon solar cells have the flight heritage that NASA really likes, perovskite solar cell technology is improving at a much faster rate than any other type of solar cell has in the past. Another benefit to perovskites is that they are extremely flexible and lightweight, meaning that they have a very high specific power. Specific power, or the power-to-weight ratio, is a crucial measurement of performance when talking about anything being launched into space. Specific power is defined as the power output of something divided by its mass. The main concern with perovskites is how fast they tend to degrade in moisture and oxygen. Obviously, on Earth, this is a huge problem, but in space, the solar cells won't be exposed to any moisture, and the only oxygen will be atomic oxygen in low Earth orbit. Part of our mission, to ensure that our comparison is truly only on the type of solar cell, is to encapsulate the perovskites, so that while they are waiting in the clean room, and even being exposed to the oxygen in low Earth orbit, this will not be a factor in their efficiency. Figuring out this encapsulation is the key to widely using these solar panels on Earth. Since perovskites degrade so fast, it is not feasible for them to be commonplace. They would need to be replaced too frequently to be cost-effective. However, if some form of encapsulation is created that would protect the cells from moisture and oxygen without hurting their efficiency, perovskites could be the next big thing, not only in aerospace engineering, but in green energy.
For our electrical subsystem, we get a really neat opportunity of using a fast bus that has a lot of the electrical power systems included within the EPS. While designing the electrical subsystems, this allows our team to not have to worry about a lot of the flight critical systems to the CubeSat, because we know the fast bus has high flight heritage hardware. The main task of the electrical subteam is to create systems for our solar panels to communicate data and power to the EPS radio on board the fast bus. And in order to finish our designs, the team will have to fabricate custom circuit boards to make sure our electronics are nice and tidy. Because we are using solar panels and testing these newer experimental solar panels, we need to be able to measure the power output from both the silicon and perovskite solar cells. In order to do this, we are measuring the power output at load due to some hysteric current voltage behavior observed in perovskites. We are going to do this through an ammeter and voltmeter, which measures current and voltage respectively, along with doing some simple math to calculate total power output. Since we are directly comparing silicon solar cells to perovskite solar cells, we need to make sure that the two panels are receiving the same amount of light or flux through these solar cells. The way we are accomplishing this is by making sure each pair of silicon and perovskite cells will be mounted on a parallel face, and each of the faces of the CubeSat will be split between perovskite and silicon solar cells. Through doing this, it will be a really fair fight, so to speak, between the two panels, making this very easy to calculate which solar cell produces more power and is thus more efficient.
Today I'm going to talk to you about the mechanical subsystem design for the Big Red Satellite 1. For the mechanical subsystems, it is split into three main parts. That is the actual mechanical design for the 1U CubeSat, the thermal control systems, as well as the attitude control systems for orienting the satellite in orbit. For the actual mechanical design, there's not a lot of decisions we need to make. With the 1U CubeSat, there are a lot of specifications we have to follow for it to count, such as having a 10 cm by 10 cm cube. We are also using a fast bus model to handle most of the physical design for us, such as the electronic supports and the actual frame of the CubeSat. For the thermal control systems, we have two main options, active and passive. In our case, especially for the size of our satellite, passive is definitely preferable as it takes up way less power and way less volume in the CubeSat. We have four main passive systems: thermally isolated structural joints, multi-layer insulation, copper straps for the circuit board, as well as a heatsink that is built into the 1U fastbus model. For the active thermal control systems, we have the cryo cooler, which will cool specific parts such as the CPU should it get too high in temperature, as well as a radiator that is built into the 1U fastbus model. The attitude control systems are also split into active and passive. For the active system, we have magnetorquers, which produce small magnetic fields that push against the Earth's magnetic field to give us active control in orbit. And using this system, we can have our CubeSat always facing the sun, for example. Our passive system is a permanent magnet which we can choose to have built directly into the 1U fastbus. This uses a static magnetic field through the permanent magnet to provide a constant torque against the Earth's magnetic field. And while this doesn't give us direct control, we don't need to worry about it flopping around aimlessly in space. We can have the permanent magnet included in the 1U CubeSat, but the magnetorquer we'd have to build in ourselves. We are currently planning on using only the permanent magnet, though we might choose to change this later, but as of right now, we're choosing the passive system. Included in the fastbus is just the radiator, the permanent magnet should we choose to add it, and the heatsink. For the multi-layer insulation, thermally isolated structural joints, and copper heat straps, we'd have to build those in ourselves. And we already have a list of companies that not only NASA trusts, but we know that we can purchase them from should we have to. But we wouldn't make any of these from scratch. We'd purchase them and implement them into the CubeSat.
The NASA CSLI, or CubeSat Launch Initiative, is a program put out by NASA to provide launch opportunities to educational institutions and nonprofits. Through doing this, NASA is able to perform low-cost research through students and engage the next generation of aerospace professionals. In our case, NASA CSLI is providing the Big Red Sat team the ability to perform research on perovskites, as well as providing us with a launch opportunity to put our CubeSat into orbit.